Hello, I'm Hari Nair, engineer at Dell Technologies. I lead architecture for the Commerce Services Group. We are based out of Austin, Texas, and I live pretty much there as well. So today for the 10-minute talk, I'll be covering at a very high level how our architecture has evolved, specifically how it was enabled by graph technologies. We've been using graph technologies for about 4 years now. Starting with a proof of concept, we have since productionalized multiple systems that use graph one way or another. You have seen or read about classical use cases like knowledge graphs and such. My aim is to go on a bit of an untrodden path here, hoping to achieve the many ways in which connected data and graphs have helped us transform our systems. Having said that, let's look at the two areas I'll be covering today, specifically two high-level areas. One is how graphs have helped in our data journey, and two, how graphs have fundamentally transformed our systems. I'll spend more time on the data journey side of the story. This is about how we evolved our systems from monoliths to microservices and ultimately to a true service cloud. The second side of the story is a transformation story, is how individual systems or processes have benefited from using graphs and connected data. Some of the ways to use graphs, traversals, graph algorithms, etc. I do understand that some of these are very deep conversations, but I'll try to deliver as much context as I can with the high-level slides that we have in place. With that said, let's dive right in. Okay, let's start with the data journey side of the story. So this slide shows at a high level how we have tried to improve our system scale and performance characteristics. So I've tried to represent a very, very simplistic three-layer model here. I'm not going uber heavy on architecture here. I'm just trying to drive a concept here. So we have the consumers, ultimately the people who are going to, or the systems that are going to consume our services up on top in blue, the services themselves in red, and the dependencies that are producing data or other common services to these services in green. Going from left to right in the picture, and ignoring monoliths and stuff that came before, we started with a typical SOA model here. Services calling other services. You have dependency services, the main services that the consumers connect to, so on and so forth. While transforming from monoliths, this gave us a lot of benefits. This still had a significant problem. This was availability in series. The availability of the system as a whole here is a function of the main service and all of its dependency services as well. Now, this makes it hard for us to achieve some of the high availability numbers. Also, from a data perspective, the data is at rest, still stored as how it was authored. Now, some optimizations can happen, and we've done that, but fundamentally, it is authored data waiting for services to transform them for the end users. So performance here again is a function of all the services in the call stack put together. Now, to address this, we try to invert the flow of data from the service to the dependency, the other way around, from the dependency to the service, where it becomes a data source. The association of the service and the dependency for this to happen needs to happen ahead of time, right? So before the consumption happens, it needs to happen. This makes availability now simply a function of the main service itself. And by processing some of the response stack ahead of time, we get some performance improvements as well. Now, this pre-processed data is closer to being consumable and is a step beyond the raw authored data that we saw in the left side of the story. Lastly, to be truly cloud and truly infra agnostic, we created the ability to send this consumable data closer to the consumer itself. So think edge processing, think instances that are made specifically for a specific type of consumption, etc., etc. Now, this gives us truly availability in parallel. We could create multiple edges serving single customer, creating redundancy between those instances. And we can also, by separating instances from each other, create fault isolation. This enables our systems to really hit the higher nines of availability and performance characteristics. Now, we are also, by sending the pre-assembled data to the edge is simpler and scalable as well. Now, let's look at how graph played a role in all of this. Now, coming to the role of graph, what we quickly started using graph for is to glue the separate systems that we had in our enterprise. So by interlinking entities that were previously stored in separate databases, Graph unlocked the ability for us to bring this data together for the purposes that we saw in the previous slide. Using Graph exclusively to store relations between entities and augmenting with other database technologies to store details, we were able to bring data that was previously disconnected together. Let's dive a bit in detail here. Say we have a service, let's say that it is managing some entity, let's call it A. Let's also say that it depends on two additional dependent entities, B and C. Let's also say that in history, A, B, and C were big enough that and diverse enough that it had to be stored in separate systems, and it's managed separately as well. We have a lot of examples of those, right? So now traditionally, when trying to serve a consumer, the call stack starts with A and involves invoking B and C, and both B and C has to produce output specific to the instance of A that is being asked for. With Graph, we are able to represent A, B, and C as relations. Now, by traversing from A to B and C, for any given instance of A, we can discover the complete data context for the specific instance of A. This can be then sent to the edge to be served as needed. So in a sense, we are using Graph as a processor. Graph converts authored data to consumable data. The output of the Graph traversals are then sent to the edge. Also, when any of the entities change, we can traverse our way to its associations, figuring out exactly what is being updated. We can think of this as like a true depth-first traversal to dependencies, right? So if B changes, C changes, or A changes, you can exactly find what was impacted by that. I'm basically talking at a very high level here and ignoring some of the other engineering that we had to do to achieve this this task. Some of the common examples, we had to deal with was, typically dependencies are modeled as logical expressions, and graphs are different than logical expressions because in a graph you expect every node to be equally weighted. So, to build those conditionalities of ands and nots and ors and nesting, we had to build some systems that are capable of interfacing that with the graph. Now, the advantages of Graph over some of the other tech, with Graph, we are getting a true point-to-point traversal system, right? When any of the vertices change, as we talked before, we can quite easily find its impact in a depth-first way. Also, being truly schemaless, the data set we are using can be changed quite easily. New behaviors can be added quite easily as well. And, being a graph, the traversals, we have fine control of how the traversals happen, right? So by changing very few generic traversal functions, be it written as user-defined procedures or ciphers, we have fine control of how the system functions. Now, I've got some numbers of one of the systems that we have. These are very specific to the graph database alone. I'm not talking about the whole system. It handles about 80 million reads per day and 25 million writes. Does all of this under 250 milliseconds, and it houses 241 million plus nodes and 315 million plus relations. Now, this is good in itself, right? So we got a lot of benefits of getting data to the edge. We got good scale, good performance, fine stuff. But we were able to get some secondary benefits out of this approach as well. So since A, B, and C were linked, as we talked about earlier, this cause and effect of a change is immediately apparent, which is very significant upside for authoring when we are talking about different teams working together in a workflow, so to speak, trying to keep the systems up. And since all of the attributes are available within the graph, all of these are available for authoring processes themselves. All right. Now, let's talk about a little bit more about the transformations that we've done using graph paths and algorithms. First, I want to take a couple of examples of how graphs and paths have helped transform our systems. We started by bringing together separate data entities with graph, as we discussed earlier. Once we have diverse entities stored within a graph, we could take advantage of the traversal ability of the graph to deliver significant outcomes. The first type of transformation we could do was forward chaining. Let's take an example again, right? So say we have an entity A that is governed by entity B. Like B has rules that manages the state of A, for example, like a validation system. Now, We could, by mapping A and B together, figure all valid forms of A based on its relations with B. We expanded on this a little further and built systems that are suggestion engines, auto resolvers, etc., etc. Now, this did, of course, require systems beyond graph, but being stored in a graph and the connected data was pivotal to being able to do this. So that's the first example there. Now, the second thing, it may not be very obvious to someone who is just starting, but this one is truly revolutionary for us. What it really lets you do is we can start your traversal pretty much anywhere in the graph, right? So you can find any type of label, you can find any type of specific node, and then you can traverse any which way that you really want. So what you're really getting is the ability to pivot and project your data on any attribute, because all of these nodes are either going to be a table themselves or attributes in a table or columns in a table, whatever you want to call it. So now we have the ability to start anywhere and go any which way and project the whole data context around that data. This is truly powerful because traditional databases do not let you do this. And in reality, what it means is you can find new service domain really, really easily. All right. Okay. Now, to my last example here. We've put graph algorithms to work to transform some of our systems. Here are a couple of ways in which we did this. The first example I want to touch upon is community detection. As we all know, algorithms like Louvain and PageRank can be used to figure the connectedness between entities. The real life examples of systems could be stuff that are connected, entities that are connected with common sets of relations. There could be value in knowing what entities are connected more to each other than others. So community detection derives local pools of nodes that are connected to each other and gives them unique community IDs, right? So it is also possible to derive directionality between these communities. So you have a bunch of nodes that are separated. Now you've figured what is connected to each other more strongly than others. Now we've figured the directionality between these communities as well. Now, this could be very effective in various use cases, like human or machine networks, for example, right? So you really want to know what group of people are talking to each other, what machines are talking to each other to achieve a certain task. In anywhere where we want to know local connectedness and directionality, this is very powerful. Now, this last one I want to touch upon is similarity. So if you think of state, right? I mean, there are a lot of places where states are really important. If you think of state as a path, right? So every unique possibility and groups of possibility are represented as nodes, and there's a head node, so to speak, or a specific label that speaks about the entity itself. Then we can use similarity algorithms to find the unique states that are most similar to each other. Now, we can also find out how they vary. This can be beneficial in any system that uses atomic changes in state to deliver value. Now, that brings me to my final few thoughts. So connected data is everywhere. We need to be able to find the breadth of our data as much as we do the depth. And graph is a truly crucial tool towards this. So, be it knowledge graphs or some of the examples that I've used. So again, as with any technology, graph has a reason and a purpose. So please do experiment and learn and be ready to change as you go. Well, that's it from me. Thank you.